So here's an example of a weak acid. So I already did this one, and here you can see I got those equilibrium arrows drawn. I just drew them both the same length, which is fine for now, okay? But now notice here, a weak acid is still a proton donor, okay? So we have to remember that acetate, right, is CH3COO minus plus H plus, okay? And it's this H plus that reacts with the H2O to make H3O plus and CH3COO minus, okay? So now when I go to write this reaction, the shorthand notation of this reaction, it's really important to note that I have to keep the CH3COOH together, even in my shorthand reaction that later I'm going to call the net ionic equation. I have to keep this together because since it's a weak acid, not all of it is dissociated. And in fact, the vast majority of it is undissociated. So I would write this shorthand, by dropping out the water, I could just say CH3COOH is in equilibrium or reacts to form CH3COO minus AQ plus H plus. Okay, so this is one example of a weak acid that I want you to know. All right. When we get into Chem 110, there's going to be tons of weak acids that we talk about. But for this class, this is the example of a weak acid that I want you to know. Okay, and then similarly for our base, a weak base example is ammonia. Okay, so I know that you all have dealt with ammonia at some point in time or another. I hope you have. I hope you've at least cleaned your bathroom once and you've got the ammonia spray. Okay, that's a weak base. All right, and so if we remember what our definition of a base is, it's a proton acceptor. Okay, so now when we see ammonia reacting with water, okay, in this case, ammonia is our base, and now water is our acid. Okay, so I mentioned that before, that water can act as an acid and a base. When you react water with an acid, water will act like a base. When you react water with a base, water will react like an acid. So what's it doing? Well, it's donating a proton to the ammonia. And now look what happens. So if I take one of these protons and I add it to NH3, it has to become NH4, but also I remember my protons are positively charged, so it has to become ammonium. So if I add a proton, not only am I changing the number of hydrogens, right, from 3 to 4, but I'm also adding that positive charge there. Let's erase that so later on when I export it, it looks clear, right? So you're adding an atom and you're adding a charge. And then now when we think, what happened to water? Well, if water is neutral, H2O, if I remove a positive charge from it, it has to become negative. And so it makes hydroxide. So we can actually see in this weak acid example, weak base example, there's two definitions going on. There's that the base is a proton acceptor. The ammonia is accepting a proton. But it's also, number two, making hydroxide. Okay, so that's pretty cool. So the other example that I want you to know for this class for a weak base is the following. And when we write this reaction, we usually always keep the water as a part of the reaction because that intimately shows us how the water is transformed into hydroxide. Okay, so we make ammonium and hydroxide. So these are two reactions I want you to know for weak acids and weak bases. Okay? So now, what happens? So, and this is one demo that the guy didn't do, but this is a demo that I always like to do live. So what happens when you react a weak acid with a weak base? Well, your intuition might tell you that, well, they're both weak, so not much is going to happen. But it's the opposite. Actually, when you react a weak acid and a weak base, you get even more ionization. So this gets complicated, so let's break it down, okay? So I'm going to change my arrow. So I'm going to use red for acids, and I'm going to use blue for bases, okay? And so here is my base. So I'm going to highlight all my bases so we can keep track. And I'm going to highlight all of my acids so we can keep track of those. Okay? So now let's see what happens here. All right? So the acetic acid, so I know I wrote it down slightly different here. Apologies. So the acetic acid, right, the proton goes to the water. Okay? An acid is a proton donor. All right? So now my H3O plus is an acid. Okay? So now what is going on here? So let's go back to the ammonia. Okay? Well, my ammonia is accepting a proton from the water. Okay? And then now it makes hydroxide, which is a base. Okay? So now what happens? Well, look, we have a very small amount. So I'll say, I'm going to go to black here. So we have a very small amount of the acetate. Remember, because this is a weak base, or weak acid, excuse me, so not all of it dissociates. So that's a very small amount, okay? And my NH4 plus, that is a very small amount as well, okay? But so now what happens is we've got this hydroxide, which is still very small. However, the hydroxide can now react with the acid. Okay, it accepts a proton from the remaining acetic acid to make H2O and even more of this ion. And then the H3O plus, we got the H3O plus from up here, okay? It donates a proton to the ammonia to make even more NH4 plus, all right? So what we are left with at the end of the day when this reaction goes is ammonium acetate, okay? So that's pretty confusing. I know that's pretty advanced stuff, but so this is what's happening with the weak acid and the weak base. We basically, I'm going to use the word titrate, and I'll introduce that to you next. We titrate out all of the H plus and hydroxide, and what we're left with is NH4. I'm going to write it differently, and I'll just put a parenthesis around it so it's not as confusing. What we end up with is ammonium acetate, cation, anion. Okay, and it's dissociated completely. That's what the aqueous means. Okay, moving.